Okay, so well, sorry for that interruption. We were expecting a fire alarm at 2 o'clock, but that one was not expected. So sorry for the interruption. Sorry to those online. But now to wake us up and get us back to the afternoon. We have Mark Randall, what's he going to talk about? Mark, we're going to talk about Australian national guidelines. But Mark is probably one of the most experienced people I know on surface velocimetry. So always got some interesting stuff to talk about. So Mark, go.
Cool, thank you, Nick. Right, yes, my name's Mark Randall. I work for the Queensland Government in Australia. Some of you have met me before, but if you haven't, hello. And I'm going to be talking about mostly about the guidelines that we introduced last year into Australia. So I'm going to give a little bit of how we got there and the sort of process and evolution of that, as well as the actual sort of standard document and a few main points. Okay, next slide, please. So just to begin with, I'm just going to sort of rewind and just talk a little bit about hydrometry and high flows. Next slide, please. So back when I first started working with the department, high flows were pretty much undertaken using a cableway of some sort with a current meter weighted down with a weight. They would drop down into the river, sound the depths, and then various corrections applied, velocity profiles applied to calculate the discharge. Next slide, please. Then, as we sort of progressed on to Adcps, and these were really have been a game changer. Probably the main way, as most of you know, that high flow measurements have been undertaken probably with our department for the last 20 years. And the progression to Adcps was a bit of a game changer, really, because suddenly now we could see what was happening under the water surface, velocity profiles, all in 3 dimensions, as well as mapping the bed at the same time as well. So really the need for those sort of velocity profiles, knowledge, kind of disappeared with the Adcps. A lot of the time, until the invention of QRAD, we were just using 1/6 power. Surface velocity measurements, they've always been around. They're not a new concept. And certainly in Japan, they're very much the main method that they use to measure their high flow events. Using floats, tracking them down with their time over distance, and applying the various coefficients. So it's not a new method. Surface velocity method has been around for a very long time. And the evolution of those surface velocity methods with the imagery methods, it's kind of an innovative approach to a traditional method. Now, you can see here using a drone to drop the floats instead of using the bridge. But yeah. So it's evolved with the cameras and yeah, the development of those sensors. So despite the advantages, we still find there's uncertainty for image velocimetry methods, surface velocity methods. Compared to traditional methods, we've gone through a little bit about the advantages that they can give you, the imagery surface velocimetry methods in regards to costs and using them, but there's still seems certain uncertainty in certain areas. In Australia, we've adopted them fully. We're happy with work with the methods, and the same as in Japan, New Zealand, France have been using for probably longer than any of us with the imagery techniques. So, what the possible causes of uncertainty and the confusion that I generally hear is, well, it's a software-based method for a start. So there's a lot of software programs out there. Very easy to put image analysis algorithms together, and the naming. So you get, along with a lot of programs put together, a lot of papers being written on. Naming can be quite confusing to people. So, for example, LSPIV, GTV, STIV, KLTPIV, SSIV. Don't tell you very much about what's going on. So, so as I get onto the standards show, we'll concentrate more as what is the actual underlying methodology, what's going on at the heart of these softwares. Not so much the name, but yeah, what's actually going in. But we do perhaps find that people getting confused with the different methods, and that can affect the results that you can have. And I think, as I mentioned before, we're very accustomed now to Adcps, where we've been spoiled. We've had the luxury of being able to see exactly what's going on through the whole channel profile and measuring the bed at the same time. But as you'll see, Adcps are not always able to measure the things that we need to measure. Next slide, please. So I'm just going to talk about flooding in Australia now, and how we sort of, where I sort of started off work and moving towards the standards. So as I mentioned, I'm from Australia, in Queensland, and it's a big place. That's area high there, highlighted in blue. That's roughly my work area that I cover, some 460,000 square kilometres. Next slide. And a lot of it is very remote. We have many days travel to get around our sites. The field trip for me can be up to 14 days in very remote and sometimes quite hostile terrain. So access is obviously a bit of an issue for us, especially when you want to measure high flows. And as you can see, yeah, a long way from nowhere. Next slide, please. And you can end up getting yourself into quite a bit of trouble. So, yeah, moving on to that. Yeah, so imagery techniques, they're very appealing to us to be able to handle those situations. This, we get flash floods. This is an example of one that happened in 2011 in the town of Toowoomba. But flash flooding, yeah, how are you going to measure that? Getting staff to actually measure that with an ADCP, very difficult. As well as flash flooding, we also get big floods. This is an example of one not too far south of us in Cairns. Yeah, within a couple of weeks of us setting up the camera, we had a record flood event go through there. So accessing these floods, again, roads are cut, the size of the floods makes things challenging for traditional methods. Next slide, please.
Should I restart it?
You can restart if you want.
Yeah.
It's up to you.
Oh. Right, okay. Sorry about that.
That's okay. Ready for the night. Yeah.
Oh,
Turn this out.
yeah, so like,
Next slide.
I'll just put the volume off for any free.
Yeah, I don't think many others actually. Oh,
I just need to start sharing it.
gotta go backwards.
Oh.
That's the one.
Yeah.
Sharing it.
And it's cancelled sharing, sorry. There we go, yeah.
Sharing.
Yeah.
Okay, so as well as big floods, we do get very huge floods. From Flinders catchment a few years ago, the river system there was about 60 kilometres wide. So again, imagery techniques can be used to measure these sort of floods. Well, Nick's going to be explaining a little bit more about potential methods for that later on. But again, all challenges for the high flow stage records, which for us are very important in this country, things like flood harvesting and environmental aspects to monitor. So, but just part of the challenges that we face. Next slide, please. And all of these floods are costly. The recent floods that we had in New South Wales and southern Queensland, the fourth most expensive disaster in Australian history. The town of Lismore, which I think has undergone some more floods recently, estimated $1 million to build that town.
Oh, sorry.
No, that's all right. Yeah, so it's all challenges. So as I say, when you're faced with sort of environments like this, you know, you've got through the rain, you've got to decide how you're going to measure these techniques. You can't do that with traditional methodologies. Next video. And again, this is another example from Pakistan, floods earlier this year. And these sort of events, this is the prime information you need to collect for modelling. And this is when rivers are at their the most dynamic, with most damage. But yeah, cannot be done with traditional methodologies. Next slide, please. And again, from Europe, a year or so ago, again, really important information for modeling. This is what surface velocity can provide you. But again, so applying the surface velocity methods to these sort of videos that you can collect and use yourself or through crowdsourcing, you need to have some level of confidence in the methods that you're applying, so you know the data you're getting out, and you're not able to validate it on site. You need to have confidence in that. Okay, next.
Oh, it's crashed again.
Too many videos for you.
Yeah, maybe. Yeah, it's crashed on my screen. All right.
Could we possibly ask a question?
Yeah, go for it.
Sounds like we're speaker. Here. So do you do more measurements now when you have surface velocimetry methods compared to when you used ADCP?
Yes,
Yes.
we do.
So in the order of twice as many or
So I'm just thinking back to one of the last floods that we were doing. We were there for a couple of days. What we would do an ADCP measurement every 2 or 3 hours, but in between that, we were doing multiple drone measurements. So I'm processing those. So we had a few ADCP measurements for checks. But yeah, the difficulty of stringing up a bit of a cable rope system, pulley system for the ADCP was difficult. We had to watch debris coming down. But yeah, that was just part of the validation. I think we took about 40, 50 videos with the drone. So just the the speed with which you can take them. It's just, yeah.
are you building stage discharge relationships with
With the information that we're getting. Yeah, for the high flows things. So and again with the fixed cameras, I've got 4 more to go in this year in remote sites up at York. So they'll be left up there 6 months over the wet season, and then we will process the videos necessary, which is a couple hundred. The most videos are processed for one slide. So just 3 months was about 2,000 videos with the Hydro-STIV software, and just leave it to run. So yeah, typically what we've been doing is using that to find a rating and then find that rating. We're up to, we get to the next one without it crashing.
Yeah.
All right. I think that's about it.
Oh, yes.
Yeah, so as I mentioned before, surface methods, in particular imagery methods, for us with our department became sort of operationalized in about 2018. After I began using them in 2016, so we're able to validate them, use them, and now we're applying them in the field. One key thing for us is keeping things simple, keep installation simple, keep the analysis simple, and then a lot easier to get some very confident results with that. Next slide, please. As mentioned, we use the Hydro-STIV image software, commercial software. And again, it's important because it's a supported software, and any software I recommend that you use should be supported and developed into the future. That's very important as part of our QA management system, provides you confidence going into the future, but ensures algorithms and software move forward with time. Next slide, please. And this example that Daniel's question, so in regards to the imagery measurements, there's a couple hundred camera measurements there over 2 flood events within a couple of weeks of each other, both about 10 meters, 11 meters stage height. So we've measured that with a camera from just over 200 QMEX to about 3,700 there. And the black dots there are the ADCP measurements that we either had in the system already or able to verify on site. So you can see gives that, it's actually showing us that there's a bit of a loop there going on, and that loop is repeated over both of those events. So this is the sort of information that you can now achieve about your measurements and about what's happening on the site with with these techniques. Traditionally for us, Adcps measurements would have collected on the fall when things are safer to the boat in. But then you're missing that rising stage. With that coming up very quickly, these loops are going to be missed. And typically we would look to target a certain gauge height. So once we've targeted 8 meters or so, for example, then that would theorize that that's done. We'll move on and target a different part of the hydrograph. So having the confidence in the methodologies as well gives you that gives confidence in the data and what you're putting into the system. And as I mentioned before, when ABC's fails, we'll have a drone. So we began using drones in 2016. I think every one of the lead agencies has been using drones to collect discharge methods and work to develop methods to make it very simple. So my work is operational, so everything I'm doing with the imagery stuff is about making it simple and use in the field.
Even that bathymeter, that's useful information, right?
That's useful information. Yeah, absolutely. But not all that stuff is done at wherever sites we've got cross sections.
Yeah.
So, but certainly there is useful information now that the policy is not there. So after that period of using the methods and getting to a point where we're happy and operationalizing them, other state governments, which as you can see there, Australia is built up of a number of different state governments. Traditionally, they're all have their own procedures, standard operating procedures. They were keen to start using methods that we were now applying and see presentations, and they want to start applying the imagery and techniques themselves. So that was really part of the movement towards the development of national standards. Is that 2 o'clock? So why was that standard required? Well, because if we're all going to be collecting imagery discharge measurements, then it allows us to have comparison between all the different states. So we're all working to the same set of procedures. A few of the state governments, in particular Western Australia, they couldn't start using the methodologies until the standard was available. They just couldn't get the funding for obviously management. So the development of guidelines helped with that, helped with the adoption and introduction of those methods. And very important for a data quality management system that you're operating by, providing confidence to the users that you've got a set standard operation compared to sort of how things have generally been in the using software and applying different techniques, different methods. That can create a lack of confidence in what you're doing. So having a set of procedures standard is very important for that. Yes, please. So in Australia, we have all the state governments, but the federal government agency, which is the Australian Bureau of Meteorology, they're the ones that all of our information goes into. They don't necessarily do a lot of monitoring themselves, but they use our infrastructure. And they're responsible for setting national standards for hydrometry. Next. And the part of the Bureau and the part that I work with for the last 10 years, they're called WAMSTEC, Water Monitoring Standardization Technical Committee. We're a voluntary group, representatives from all the different state governments as well as the private industry. And we're responsible for pulling together these hydrometric national guidelines. There's a process that we have to go through for this and the others that we have. So the draft has to be proposed. The WAMSTEC committee has to agree that there is a requirement or a need nationally for this standard. A draft is then produced, and then it goes to industry review for 3 months. All the organisations are able to, and anyone is able to actually review it, suggest edits, agree, disagree. And that's a really important process because this is going to be applied to the industry in Australia. And then once that has happened and the reviews have been done, then WAMSTEC will endorse and publish the guideline. And at that point, it is accepted that hydrometry agencies within Australia will operate in accordance with that guideline. Next, thank you. So, as I mentioned, this was the guideline we produced for surface velocity methods. It's available at the website address up there, so you can download it, have a read. It's number 11, so we have national guidelines covering the various different aspects of hydrometric operations, so Adcp measurements, site setups, data review, data processing. So we have a set of guidelines for each, and as I said, the state governments indicates the Bureau to us how much they can apply these guidelines. These guidelines cover, we focused on the imagery methods, which really was the primary reason why these guidelines were put together. But we also covered the surface radars as well. But yeah, the main driving force was people want to start using drones. So the majority of the document focuses on those methodologies rather than the radars, to put as much information in there for people to follow. And the radars have been used for a little bit longer as well, but not entirely used across Australia. So in the development of our guidelines, we look to remain in touch with existing hydrometric standards. So ISO 748, for example, already contains certain information and regulations in regards to surface velocity measurements for floats. It's velocity area methods, so again, it's already certain standards in place that we have to align with. The last one down there, that's in regards to Photogrammetry Standards from 2014. But again, that covers an existing standard in place for scaling pixels in images. So we looked for and worked with existing criteria, existing standards, please. And as part of the review, and this was the first for our suite of guidelines, it was put out to the international community, and we got some really good feedback from some people in this room, but some have already presented. But yeah, we really put it out there, and we got some feedback. So we're picking the expertise of those around the world who have also had good experience with these methodologies. Thank you. So one of the first things I mentioned that we try to do is provide guidance on the analysis methods. So we look to sort of break it down into sort of two main areas. We call it LSPIV, but really essentially the tracking methods. So those methods that are looking to track the movement of individual particles between the frames, and then STIV, which is slightly different, it's more of a tracing movement. So it's quite a simplest way of looking at it, but essentially that's what they're doing. Some algorithms are looking to track and look for individual particles as they travel down, find those particles, whereas the STIV is slightly different. It traces the patterns of any particles, traces moving over an analysis point. So really to clarify that and set the criteria and the boundaries that you should be using depending on what core methodology you're looking at. Next slide, please. And to really get the users and the readers to understand the strengths and weaknesses of those methods as well. So this is an example of rain on your camera, whereas despite that, we were able to still process those velocities using STIV just through the nature of that algorithm. Next slide, please. So as well as the methods, we look to define criteria for setting up your sites and guidance. So site selection criteria for your fixed cameras, at best elevation, angles that they should be looking at the river in regards to width. We also look at recording guidelines, frames, how many frames you should break that down to if you're using this correlation method. So try to provide as much information there with the site setups as you can, and in terms of resolution, things like that. We also did cover drones, again, so some criteria for how to use the drones. checklists that you need to do and applying those in the field in terms of the information that you need to collect. So when you take those videos back, you're able to process and check and have confidence in the results that you've got. Next slide. Image author rectification. So we try to include information on the different types. To clarify that, something that sometimes people get a little bit confused about and what specific author rectification method you need. So three-dimensional with your X, Y, Z information, your 2D, which would just be for a fixed water level, not changing, but with an oblique view. And then your scaling for your drones, which typically is a known distance without imagery. Author rectification errors. So we try to define and using the standard that I showed you earlier in regards to pixel scaling, and looking at the errors within those ground control points to set a standard for setting up your site. You can go to the next slide. So this is in regards to standards that we set. So looking at the room mean square error for the ground control points, and in relation to the pixel sizing that you get from your rectification, how that room mean square error relates. The error relates to that point. So we had a chat with our surveyors, and again, this is something that they suggested. It's something they use in surveying when rectifying these images. Next slide. Video length or exposure time. It's again something for discussion, and something that is, as I mentioned earlier, is already defined. So in ISO 748, minimum acceptable exposure time for float measurements is 20 seconds. As mentioned, this was up for discussion. Some software already out there was used for shorter videos. But again, part of that whole review process that we had of the document and having people review the document that weren't familiar with imagery techniques. So there was an adamant opinion that you must remain with these time limits. Okay, you can't not fitting a method to that. You're fitting the method, creating the software and the measurement techniques to the accepted standards. Again, and that brings it like current reader, ADCPs, things like that. And that is to guarantee that you can cover the various conditions that you're going to meet from the higher flows to the lower flows. So having a set video length that you're using will help to define that and capture that variation. We recommend an exposure time of 30 seconds. And again, we suggested in the guidelines in regards to, for example, drone measurements, taking 4 videos and then averaging those to get your final discharge values and bring it in line with procedures you use for Transect with your ADCPs, for example. We also specified that if you were to use shorter videos, then again, say for example, you use 5-second videos, again, you'd use 4 5-second videos to meet the criteria of the guideline. We're finding similar conversations when we were setting the ADCP guidelines in regards to 12 minutes, and then 12 minutes exposure time for your measurements. We have a lot of feedback saying, well, I can collect a decent measurement in 2 minutes. And so it's kind of not the point maybe here, but there is a standard and this is what you need to stick with. So similar conversations here, but having people, as I say, not familiar with the imagery techniques, but been in hydrometric business for a long time, quite adamant that we need to stick with the standards in place. Next slide. Data interpolation. So this is looking at going across the channel. And again, it was felt there needs to be criteria in place to help assess those measurements. And again, if you were doing a current meter or a flow tracker measurement, you wouldn't measure half the channel and then interpolate it back. So there was a strong feeling that standard must still be applied to the imagery techniques. So the quality band, obviously quality band 1 is good, down to 4. But again, it's about getting those algorithms and choosing the right algorithm or software to measure as much as it will measure the channel properly. And so, getting your setups right, really, where these things will work. That's the slide. No, sorry. And that's just an example of that, where velocities can be lost and interpolation between those points. So again, it's something we have in place with all the other methods. So flow trackers, current meters, you wouldn't measure part of the channel, you would measure all the channel. ADCP, we look to see how much data has been interpolated and the size of that data and where it's occurred in flow. So it's bringing imagery techniques in line with the rest of our biometric methods. Thanks. We also included guidance on surface alpha to help those people. This is the flow that Hamish actually developed over in New Zealand. So we borrowed that from which we were talking about earlier. But again, going through the methodology, how to actually try and define a surface alpha using ADCP data or channel roughness with some examples of typical values. Again, to try and better explain and help define those for people who are confused. And big part of what we do with standards are one aspect, but you need training to support standards. As with ADCPs, imagery methods are a practical method. They involve you being in the field. So you need training how to set up the site correctly. And the different aspects, a lot of what we do then, as well as comparison measurements, so that people processing the data are able to actually get a feel of how they do it. But important to support standards in place. And again, as I mentioned, not just about the training in the field, how to set up the sites and the camera and positioning and things. Data analysis is very important as well. So running through the criteria, stepping through the methodologies that we use to help, again, provide confidence in the results that they're getting when they're not able to have a measurement, a comparison measurement on site, that we have confidence in the data they've got out. So, this one. Yeah, so just as a final summary, why is standard required? Well, because it's all about consistency. It's about getting your data into a quality management system, creating confidence in that data and operationalizing those techniques. As far as I'm aware, the guideline that we put together is, I believe it's the first one out there of its kind. It's, I'd say, it's not a departmental standard operating procedure. This is a national procedure, national standard that monitoring agencies in Australia are expected to abide by. And hopefully, and there is some talk, but hopefully this will move forward towards the development of an ISO. Yeah, so thank you for that. Any questions?
Yeah. I think you told me you did 4 30-second movies usually. Yeah, usually, and can you explain that? Yeah.
So with the drone, as you say, we're usually just collecting a single measurement as you would with an ADCP, go to site, do a measurement. So with the drones, typically what we'll do is we'll hover them in place for 10 to 12 minutes, and we'll record 4 videos every 3 minutes, and then process those up and take the average of those 4 measurements, much like you do with ADCP transects. And then, yeah, just to make sure, because you capture the spectral velocity pulsing across that time period. Again, it was just part of that whole conversation with people. I'm going to go and do a measurement in 30 seconds and kind of review process. People less familiar with it. Well, no, you can't, because ADCP does it for 12 minutes. That's our guideline. So you need to be doing it for 12 minutes. So it's about accommodating, processes and making it on the same plane as accepted methodologies, the traditional methodologies.
Just to comment, it's so easy to make a video, I mean, by drone or even with your phone. That we often recommend to make, like, into the phone, to make several videos from different angles, different point of views.
Yeah.
Because, for example, you can think that one video is okay, but then you have a similar and something. If you make the video from the other bank, it could be better. So I think it's good for people to make several videos, and
Absolutely,
hopefully one of them will be okay for.
absolutely, yeah.
So, is the standard also addressing the question of uncertainty in some part that we talk about rating? But, and what about uncertainty?
Uncertainty. Yeah, we're actually waiting for you guys to develop the uncertainty. No, we talk about the areas that people need to be aware of. And so we've tried to, and as I say, try to cover those areas to reduce the uncertainty in as many places as we can. Obviously, I think the float measurements was a plus or minus 15% in one of the ISO documents. So we do mention that, but it's something that we still need to look at. I think ADCP manufacturers still only refer to their uncertainty in regards to velocity, not discharge, and that may be something that it's a starting point for the imagery. But there is the document will be reviewed every 2 years because we understand that methods evolve and more information can be provided. But at the moment, we wanted that guideline out there to standardize what was happening, allow people to start using it. And typically, like one thing that we do to look at is we'll have the 1/6 power law and then have 0.9 or 0.8 and to get a range of what the possible discharge value could be. Surface out is always something that people ask about. So we try and quantify as best we can, but it is area for development.
There's someone in the chat has one more.
Okay.
So how do you decide when to use measurements for rating curve?
How do you decide when to use that?
So is the measurement, when is the measurement good enough if you don't have a certain thing? I'm just thinking in terms of the way we do it and how we operationalize something that does not have a specified uncertainty.
So at the moment, well, typically, okay, so with the ADCPs, we get the level of the uncertainty from the COP. 4Q rev will give us a much better idea of the uncertainty. So typically, we would look to get those with the Transects within that 5%. With the imagery stuff that we use for drone, that helps why we've got the full measurements, so we can see that we've got the same thing that they're all within 5%. So that will give us confidence in that measurement. And then using the STIV, you've also got the confidence of how those traces have been defined correctly. So although not exactly quantifying the uncertainty itself, we can look and see and decide our own confidence in that measurement. Are the angles in the STIV being defined correctly? Our control points, our error, is that small enough to know that our pixel size is good? And then obviously surface alpha, we have a little bit of idea, but you can go back and change that. So typically those measures will help us decide the confidence of for example, a drone measurement, and then we can decide to use that measurement. And typically for us, plus or minus 10% of the rating curve, we're quite happy with that variation. If it's a fixed camera, as I showed you that graph, you've got multiple measurements. So yes, there'll be 30 seconds, but so you can see the train. So that provides you with that confidence that those measurements are good. And again, with using the STIV Hydro-STIV software, we are able to check those manually to see that the traces are defined. We've defined the errors with control points of replication. So it's about confidence and looking at the data and controlling all those areas where uncertainty can be introduced and minimizing as much as you can.
And also, if you resurvey the bathymetry afterwards, maybe you can be even more certain that it's okay.
Yeah, I didn't touch on it there, but again, it's in the document, and with bathymetry, we have a requirement that you survey the bed annually, and for the first 3 years, and then after major floods, and that's similar to what we do, or the same as what we do for horizontal ADCP, to quantify that. So if a big event has gone through, the guys will put out there as quick as they can to survey that with the ADCP. But at the end of the day, I mean, this is for us especially. You're talking about collecting measurements for the high end of the rating curves that you would not be able to measure any other way. So if you're plus or minus 15% that you decide upon, it's better than nothing. So many of our sites only have low flow measurements. We can't get that.
Someone in the chat, James Bomhoff, asked, what has your experience been with alpha across a range of discharges? Do you decrease alpha as discharge increases or keep it static?
Typically, we've found as the depth has increased, we're typically going to like 0.9, 0.91 of a surface alpha. So it's increased in that respect. And then on a few very deep rivers that we've done, when you're talking sort of 14, 15 meters depth, and you go back to 0.85. So it sort of drops that standard 1/6 power law profile. But again, it sort of depends a little bit on your channel shape. But typically, it's been within that region we find. And then the shallower it gets, that's when the surface alpha lowers to about 0.7, 0.6 even as that bed roughness tracks it. And checking that surface alpha when you do your measurement will give you an idea of the variation that could possibly occur. But the one great thing about the imagery stuff is that if you do collect any data that you can refer to that, then you can change that surface alpha down the line. I think the key is to get the video and get the setup and all that aspect of it key.
Yeah.
Right.
Just wondering how widespread is it used now in the other states, not just in Europe?
Yeah, so Western Australia started running with the Hydro-STIV, and again they were a big driver for the guidelines because they needed those guidelines in place for them to then start introducing it because it's now a standardized and operationalized method. Snow in hydro, it's picking up within the other states. The floods earlier this year in New South Wales, again I think they lost a number of ADCP remote control boats trying to measure those floods, and now they're looking towards the drones. So it's being picked up across the country, really.
And is it more the drones or fixed cameras or what's coming out on top?
From what I hear, a little bit of both. The drones are good because it gives you that flexibility and it's simpler to do. So yeah, and it's got that health and safety factor about it, that if you get to a site and you're not happy with flows, you don't want to risk your ADCP boat, then you've got the drone there to grab some measurements. So yeah, I think the drones is what I hear more of. But yeah, fixed cameras, certainly.
Just then on wind, we're starting to look into it, but wind is a big problem to the
Wind for drones, or the DJI ones that we use are pretty robust in wind. The imagery remains remarkably stable, even though the drone, you can visually see it wobbling around. So it's not been a huge problem. Obviously, if it's visibly affecting the water surface, then you would need to correct for that. And the Hydro-STIV new version actually has a wind correction factor in there that you can then introduce. So yeah, if you're measuring it on the ground, you can then correct for that wind. But yeah, have a look at YouTube, and there's always some guys flying DJI drones in extreme winds, so it gives you an idea.
What kind of level are they getting?
70 odd kilometers an hour, isn't it? Miles.
Well, the quoted limit on the Air2S is 10.7 meters per second.
Yeah.
Which is what? 13 seconds. Yeah.
30 kilometers.
So
Yeah.
Just over that.
it's not that high, but our wind is often higher than that when we're thinking about deploying it.
I think that's a safe. That's a
I think,
safe
yeah.
bet.
You can push it higher.
Yeah.
Measure. Charging each says by that's probably 15 on that.
Yeah. It's always higher.
But I mean, it's very balance. One of these places where it needs to be windy. I've been having all last week. On the Saturday, on the Friday, when there's still weather came through.
it was both too wet and for a while too windy. But by the end of the day, by the end of the day, by about 3 o'clock, the rain had stopped and the wind had dropped sufficiently that I put my drone and got some vision. So, I think that the thing is, you can go out and get a lot. Because very often, when we get very regular food, then it stops and it really is making rising.
Yeah.
Because
Yeah.
it's another tool. It's a fantastic useful tool. You can get way more data way more quickly. But you're right, it's really blowing down. You can't fly it if it's raining. But I wanted to ask, if you're aware of any drones. I mean, I know there are some big ones, but any relatively low cost and relatively small drones that have the ability to fly in rain.
Yeah, there's the splashdown drones, which are they're a fishing drone. They're a little bit heavier than 2 kilos last time I checked, but they're fully waterproof.
But do you think DJI will make one? Because most people are standardizing DJI because their price is so good. So
yeah, I would hope so. I would hope so. I mean, there are wetsuits, as we've spoken about before, that you can put on them. The company makes and has filmed them flying in the rain with these little wetsuits. They're about 100 Australian dollars. Just cover up the fence. Phantom 4, I've flown in some quite heavy rain, but the battery is located on the side. So I think that's the main worry, I would say, is just getting that water into the battery.
I heard of someone whose smartphone in the river.
I don't know who that
was flying again 2 days later. They told me.
Yeah. So yeah, I mean that is a little drawback with those drones. Something you do have to be mindful of. But I would say if you're using DJI, the sports mode is the high power mode. So sports mode will fly against remain stable against much stronger winds than the normal mode. And I think that's what they quote in the manual. But yeah, certainly have a look online. It gives you a bit of an idea of what you can and cannot do with them. Yeah.
Hamish has a brilliant video of his drone. I don't know what drone it was, but he has it hovering 3 meters above the ground. And he's got a hose line.
Yeah. Yeah. Anything else?
As we should move on.
Yeah.
Yeah.
Thank you, Mark.
All right. Thank you.
So we've got
We have the next session is about software. We've got 3 talks planned. One is online talk by Ken Watanabe, get from Japan.
yes.
So he's going to talk about improvement to STIV software. And then we've got 2 talks which speakers are present here. So to get Ken sorted, I think he's going to be sharing his screen.
Yes, I'll just stop.
Thank you very much. Can you hear me?
Ken, are you here?
It's
Okay.
playing on my laptop.
Okay, well, he's going to hear us.
Can you hear us, Ken?
Okay, I'll share my screen.
Sorry, I need to get your audio playing out of the speakers.
Okay, can I see the document?
So have a look at what speakers are available there. So I'm just going to.
Yeah.
That is okay.
So if you could. Just going to
Yeah, no, it's not.
Can I share the screen?
Yes, we can see your screen.
Oh, okay, so shall I begin?
No, the speakers are messing up.
Okay, hello everyone. I'd like to thank you for giving me the chance to speak here today. Okay.
So try this one. Can you say something?
Can I continue?
No, just give us a second. Give us a second. So we have a bit of an issue here. So equals others. It doesn't want to come through by something. So, go back. No bit of an issue.
Oh, yeah, yeah.
Say something. Can say something.
Okay,
Yeah.
We got you okay now. Can,
sorry,
are you with us?
I'm sharing the screen. Can you see me?
Yes, yeah, we can see your screen.
Oh, okay. Sorry. Thank you very much. I'd like to thank you for giving me the chance to speak here today. My name is Ken Watanabe from Hydro Technology Institute in Japan. I'm in charge of the development of Hydro-STIV, which is introduced in this presentation. The title is Improvement of Hydro-STIV to Measure Flow Rate with Video Footage, New Features and Portable Version. The purpose of this presentation is to let you know our software, Hydro-STIV. We will also introduce some of the new features we have recently developed, and we hope you will consider taking advantage of them. First, I'll outline the software, Hydro-STIV. First of all, let me explain the motivation for product development. This slide shows the conventional velocity measurement method have been used in Japan for a long time, as Mark-san mentioned, which we call it the float method. The river discharge measurement is very important for the management of the rivers. So in Japan, we observe discharges of major rivers every year. As you can see, in the float method, the workers measure the travel time of the float to pass from one cross section to the other. So during flood, workers have to go to dangerous flooding river and have to do the measurement in a heavy rain. It is becoming a big problem because severe floods are taking place more frequently than in the past. One alternative approach is to use Adcp shown here. It is considered one of the most reliable measurement instruments, but since Adcp can be easily damaged by floating objects during flood, we can't use it in severe flood. Moreover, as Adcp is very expensive, so it is difficult to use it at many measurement sites at the same time. As I have just explained, we have many problems in the conventional velocity measurement. I think and believe that the image-based technique can solve these problems. Since these techniques use video footage, it is safe, simple, and cost-effective. Image-based methods include PTV, LSPIV, optical flow, STIV, and etc. All methods have their advantages and disadvantages, and STIV is the superior method in terms of computational speed and robustness against noises for measuring surface velocity in the main flow direction, which is necessary for flow measurement. STIV was developed at Fujita Laboratory of Kobe University in Japan and published in 2007. STI means space-time image and V means velocimetry. A brief description of the methodology is provided here. The first step of STIV is to set the set line, this red line, in the direction of the main surface flow. Then construct the STI by filling up the image intensity distribution on the set line. Please see the left pictures. As you know, video consists of a series of static images. So 30 FPS includes 30 frames in 1 second, and 10 seconds video consists of 300 frames. This yellow line is such line, and let's assume that the red floating object moves along this such line. When we stack all the such line vertically, we get a space-time image. STI. STI shown in the right figure. When the red object moves at a constant speed, we get a straight texture in the STI. Since the particle flows down L meter in t seconds, and it means surface per velocity is L over t. Therefore, by measuring the angle of such lines or stripes appearing on the STI, the corresponding flow velocity can be determined. This is an overview of the STIV methodology. Today, I'd like to introduce our software Hydro-STIV, which measures surface velocity based on STIV method and calculate river discharge. The appearing point of Hydro-STIV are its easy to operate user interface and AI estimation, which makes it easier to use without tuning analysis parameters. In addition, we can use it for 24-hour real-time monitoring using an infrared camera. The STI in the center were each created from the video on the left. As you can see, these STIs have complex patterns including shadow, light, and wave. So it is sometimes difficult to get appropriate angle of the stripe pattern automatically when we apply the conventional automatic detecting method in STIV. So we try to apply deep learning technique to obtain the angle of the pattern with good accuracy. Good estimation accuracy was obtained after the deep learning was trained on about 200,000 STI datasets. This slide illustrates the improvement of the automatic measurement function by deep learning. Top pictures the video footage and bottom images are STIs made from them. The yellow arrow is the correct answer by manual, and red arrow is the result obtained by the deep learning. Blue arrow is the result obtained by the conventional method. As you can see, deep learning yields more robust measurements than the conventional one. I'd like to move on to applicable example of Hydro-STIV. First, as an example of STIV accuracy verification, we present a case study comparing it to ECM. ECM means electromagnetic current meter. The photo showing people making observation by ECM. Blue dots in the graph indicate ECM data, and red line is STIV measurement. As the graph shows, the STIV measurement agrees well with the ECM data with a relative error of 1.4%. Next, this slide shows an example of night observation. The top image shows measuring using far infrared camera. The river of the right image is urban river and can be measured by visible light camera even at night because street light illuminate water surface. Next slide is about the measurement using drone. Drone-based measurement allow for flexible selection of flow observation area and enable observation in areas that are dangerous and inaccessible. This makes it useful when the river is too wide to capture its full width from the ground, or when access to the river is dangerous due to flooding. The last example is measurement using trail cameras. Trail cameras are low cost and usually can stock and communicate data taken at regular intervals. It's making them useful for monitoring small rivers. Trail cameras generally have a maximum range of 15 to 30 meters, so they are intended for narrow rivers and the camera must be close to the river. I'd like to move on to new features and portable version. We released Hydro-STIV cloud version on June 1st of this year. Unlike the USB dongle version that we have provided, the cloud version supports remote use and simultaneous use by multiple users by introducing a network authentication function. It also includes new features such as wind velocity correction, cross-sectional velocity distribution estimation, and enhanced drawing and output functions. In addition, while in previous version, it was necessary to separately input measured values for water levels, a function to measure water level using images has been added. This function automatically detects the water's edge in the image and measures the water level based on the watermark information. We have also developed a portable version that allows surface velocity measurement without the need to survey a ground control point at the site. By getting camera angle information from the tablet device's internal acceleration sensor, measurement is possible simply by inputting the camera height from the water surface, simplifying the geometric correction process. Here is an example of the accuracy verification of a real river, which is 140 meters wide. In this case, the tablet version of the measurement yielded almost equal results to those obtained from Hydro-STIV crowd analysis of the drone video, with a difference in flow rate of about 3% or less. The portable version is undergoing testing and verification and will be available soon. Here is the conclusion. I have introduced our software Hydro-STIV. This software achieves robust and accurate measurements through STIV with deep learning. In addition, its user-friendly interfaces makes it easy to use. And Hydro-STIV can be used in a variety of situations, such as nighttime and with drone and etc. We have updated the software to add new features and are preparing to provide a portable version. Thank you for your kind attention.
Thank you, Ken. Any questions? So, to see, should I?
Yeah, you might need to go a bit closer to the that's right. The microphone's up. Thanks.
Actually, I was wondering if we could get more details about the wind correction, and then maybe
Yes.
also about the camera calibration only using accelerometer. So you get three variables, and how can you calibrate with three variables?
Yes, first one, wind correction is a very simple function. So the simply multiple the coefficient user setting to the wind measured and input to the software. And calibration, simply calibration, the devices in an acceleration sensor. From acceleration sensor, we can get the tablet angles. So the intrinsic camera parameters from the API. So we just need the water level height. So that is need to be input.
Is it answer the question? Yes. Okay. So anybody else?
Yeah. Yeah. Oh, you got. Oh. Yeah. Thanks. Thank you.
Hey Cam, just a question: if the flow is not uniform, for example, it's the velocity are increasing or decreasing in the image, then you won't have a straight line, I imagine, and it will change. So is there a way in the software to reduce the size of the, I don't know, you call it the 13 segment, something like that, to be sure that the flow is uniform in that segment, or how do you deal with is increasing or decreasing? Thank you.
Thank you. About wind, we assume the static uniform wind speed. We assumed. So not so complicated correction is not used, cannot be used.
And can you change the size of the searching segment?
Can you change the size of the searching segment?
Sorry, I can't hear you.
Can you change the size of the search segment?
The search line,
Search line.
you can adjust the length of the search lines. I have an example of presentation later on where we have varying velocities within the search lines. So we could talk about it then, if that helps. Ken, I have a question. Can does the mobile work?
水面幅とか変わっていくときに、それが追随できるかどうかっていうようなことを聞いてると思います。水深が低いときと上がった、はい。
なるほど。It depends on the speed. So water level change. So it's difficult to answer. I'm not so sure.
Okay, can I ask a question about the portable version? Does it work on any device? Is it you said a tablet, but do you mean like a tablet, like an iPad size thing, or will it work on a phone as well?
Thank you for the question. Now we designate the tablet device because if device changes, the camera resolution is changed, and we can't ensure the analysis accuracy. So now we provide only the designated tablet provided by the Panasonic.
Okay.
In Japan. Yes.
All right. Thank you.
Thank you.
We probably need to move on. Thank you so much, Ken. Thanks for being patient with us as well. So because of the fire alarm. Okay, Alexander.
Okay. So I think that Nick will like the first slide because you know who will pop up on this slide. Sorry, one second. Sure. It will be a short presentation just on, very short. Ready for the 10% now? I just need to get, sure. Yeah, this one. Yes, yeah. Okay, so just a short presentation on another software that we are developing with some colleagues. So Guillaume, who is in the room, but also other people, Jérôme Lecause, Magali Jodot, Bertrand Champ. So the software is called Fudaa-LSPIV, and I will mostly to focus on what's new in this 1.9.2 version. So please. Yeah, so I think that you understand how it works. You need to make some videos of a flow. So it can be any kind of video. I said drone is very useful, but if you don't have a drone, you can also make a video with your smartphone, with whatever you have. It's going to be okay. It can be used for fixation. Next one. And then the software will start by stabilizing the video, especially when you are doing videos with drones at low altitude or with handheld smartphone, moving a little bit. So the software can stabilize, and we use a stabilization algorithm that cover the river because you don't want to stabilize on moving object like the river, so you need to cover it. Okay. Then once the images are stabilized, the software can auto rectify the images. So it can handle rectification from oblique point of view like this one. So using 2D or 3D auto rectification. So I think that Mark talked a little about that, but 2D means that you only have the water-free surface is not moving, it's not changing in time, and so you can use only 4 reference points located at the same altitude than the free surface. But you can also use a 3D rectification, meaning that you have GRPs, so ground reference points, with 3D coordinates, X, Y, Z. And at the end, you have these auto images, which are images as if they were seen from the top. Okay, next one, you can also use a simple scaling when you are using a drone and the camera is pointing to the nadir. So you just need to know a distance. For example, in that case, we use the size of the truck to correct, or you can have also like size between 2 known objects, like this, the bridge pier and this pole. And it's enough to make the rectification. So it makes the rectification much more easier using a drone. Okay. Then LSPIV, the principle of LSPIV is that it will follow some patterns of the flow. So in PTV, you try to track some particles. In PIV, you just look at an interrogation area of a known size. You look at the pattern in this interrogation area, and you will try to find the same pattern in the next image. So if you just go one more, and that's for explaining how it works. I mean, it's that's the interrogation area, and try to follow the head of this guy. So it's not the software. It's not what is included in the software. But like that. Okay, so at the end, you have instantaneous surface velocity. Disturbing, in fact. You have an instantaneous surface velocity field for each pair of image. So, and you can see that it's a 2D surface velocity field. So that's the strength of this kind of method, PTV or PIV, is that you can measure a 2D surface velocity field instantaneously over a large area. So that's good results. And you can, if you want, next slide, you can also time average the surface velocity field. If you have 20 or 30 seconds of video, then you can time average to have the time average surface velocity field. And if you know the bathymetry of one or more cross sections, and if you have some assumption about the link between the surface and depth average velocity using magical alpha coefficient or something else, then you can compute the discharge. So in Fudaa-LSPIV, you can have several cross sections. You can also use several alpha coefficients. For example, you can say that close to the banks, it's maybe rougher than in the middle of the river, which is smoother. So you can use different alpha values depending on where you are in the river. And the software at the end will give you this kind of table. So for each cross section, you will have some results about the total discharge, the weighted area, things like that. And so you can compare the results from the different discharge, from the different transects together. Okay, that's the LSPIV. You can go to the next one. And yes, and you have a report which is created, which look like for the people who are using ADCP, it looks like the Wheel River report, something like that, where you have all the information about your studies and the results that you have. Next. So the software is free and open source. We have a Windows and the Linux version. We are working on the software since quite a long time because the first version was in 2009. So it was a lot of development since 2009. We are 6 people involved in the software. That does not mean that you have 6 people working full-time in software, just we are involved in other things, but we are 6 people involved in that. And we have researchers, like some of you may know Jérôme Lecause, who is a researcher working on that. We have field hydrologists like me, but also computer scientists that help us to make the software efficient, because when we make the code, it's not efficient code. So we have to have someone who knows what he's doing to recode everything and make it clean and efficient. We try to give a free, we give a free, but try to give a quick assistance when you have questions. So we have a lot of questions coming from people. We don't know exactly how many users we have because we don't track. We are not tracking very clearly the people, but I mean, the last version of the software was downloaded nearly 1,000 times, but we think that we only have 300 real users of the software. So, it's a lot of time for us to make the assistance, and we take a lot of time by responding to email or something like that, but it's okay. We have an annual training in France and in French, so if you want to practice French, that's a good way. But I mean, if you need some assistance or some training in other country in English, it's possible. You just need to accept this French accent. The software is in French and English. If you want more languages, it's very easy to add because it's the way it was written. It's really easy to add new language, just tables. It's quite fast computation thanks to our computer scientists. And as I said, it's an evolving software. So we try to have, I mean, the last version was released in May this year. And you can see it's 1.9.2, which means that the last version appeared. And we try to take into account the user request. I mean, if you have some needs or something that you see you'd like to try to do it. And we also have a script version. So what I showed before was the graphic user interface version, but we also have a script version which can be used for fixed LSPIV station. And we are very happy to share the code with everybody. Okay, next slide. So we hope it's a software you can trust in because we have been applying it for a long time. It's open source. We have a lot of publication related to the software. And we have a lot of operational hydrometric agencies in France, but also abroad using the software. We also like the software to be, I mean, open source and completely nothing is hidden. So you can just check all the computations, and if you think that something is not good in a proper way, you can exchange with us and we can change the things. Yeah, you have the user has a control of almost all the calculation and filtering parameters, which can be a little bit scary at the beginning because it can look complex. So now we are also working on trying to make it more simple. So it's part of the PhD of Guillaume here to make the software more simple with more default parameters. And you can make some nice visualization of the flow. Okay, and it can be used for a lot of operational and research application. I mean, we use it for discharge computation, but also, as I showed this morning, for just mapping of complex flow. So, for example, for validation of 2D or 3D hydraulic modeling. People also use that for the computation of instantaneous velocities for turbulence computation. I don't understand anything about turbulence. You can use that. Okay. What's new in the last version? Finally, we just added a simplified 2D rectification. Sometime you are in the field, you don't have any total station, but you may have like a laser distance meter or just a tape. And we have a way to make a 2D rectification, just measuring the distance between some points. And you can measure the distance being on the same bound. You don't have to cross the river. So you measure all those distances in red, and it will compute the location of the ground reference points. Next one, please. Okay. Something we also added to try to make the parametrization easier is a manual tracking, meaning that you can manually go from an image to the other one. And if you recognize a pattern, for example, this one, you will track it over the images manually, and it will give you an idea of the velocities that you can expect in the river that will be used to parameterize the searching area in the LSPIV computation. Yes, and last, something we also added in the last version was the possibility to use what we call this abscissa depth transect. In fact, it's very useful when you have ADCP bathymetry. ADCP will give you a distance and a depth. And using this option in Fudaa-LSPIV, you can just click on the beginning and ending point of the ADCP transect and import the distance make good and depth data from the ADCP. So yeah, that's it. So then I was thinking about making some demo, but in fact, I didn't realize that it was not my computer that was plugged on that. So that's okay. I think I will just stop with that. It's the last one. Yeah. So enough time maybe, but not enough computer. So enough time for questions. Thank you.
put 8 minutes. Yeah, really, yes. Open source means that we have access to the source code.
Yes, that's it.
Source code is.
Yeah. So there are two source code. We have the graphic user interface source code. Okay. But we have also all the scientific codes. So it's Fortran, C, maybe that's all, C++. Yeah, codes. And you can have access to all of them. So the graphic user interface, it's open source, so you can directly download it. For the scientific codes, you need to ask us, and we just share everything. Very happy to have, I mean, we are now 6 people. I just wrote my email yesterday, and apparently we have 3 more people joining the team. So we will be more people working on that. And of course, no, I mean, all the people are not involved at the same stage of the software, and some are just giving some good ideas and things like that. And we are very, I mean, we welcome people that want just to add some ideas. Yes, Nick.
So you showed for the drone method, the Nadia view, scaling using objects on the background.
Yeah.
So have you done any analysis of whether there's any difference in the accuracy of results when you use, say, river width versus an object that might be towards the edge of the frame of the image? Does that have any impact on?
Yeah, it's a good thing to do when you do scaling. It's to, I mean, the best way is to have an object which is in the streamwise direction, because it's where you want to be the more accurate on streamwise. So it's better to have a long distance in the streamwise direction, but it's also nice to have distances like in the spanwise directions, just to check if your camera was pointing to the nadir. Something else, can you go back to the view from the drone, which is very important, and that will be in the next version of Fudaa-LSPIV. Back again. No, it was all. No, yes, so, sorry, back again. You can have some issue if you use back again.
Oh, with the
yeah, this one.
Oh. Yeah.
If you use an object which is out of the plane of the river, for example, here the car, I mean, it's very close, so it's quite okay. But if you want to use the size of the bridge, which is maybe 5 meters above the free surface, then you will make some error because you try to rectify the water plane with something which is out of the plane. So in the next version, so 1.9.3, that should arrive at the end of the year, you will be able to measure a distance from a bridge and give the height of the bridge to the water, and it will correct automatically to have the right distance on the water free surface. Because we had a lot of users that made that mistakes measuring distances out of the plane of the river. So your question was about, I think it's better to have several distances on different orientation just to check that the camera was pointing to the nadir, but take care of picking objects that are in the same plane than the river.
Saying it's something to do, also specifying the guidelines like the scaling points,
yep.
Also checkpoints.
Mm-hmm.
To the scaling, the other two checking that scaling.
Yeah, that's a good idea.
But it would be, you know, if the objects like those vehicles is right at the edge, it would introduce some bias compared to if it were in the center of the image, because it's further from the camera, so the pixel dimensions on them.
Now, if you have no lens distortion in the image, so if you have no, and you have to check that because lens distortion can be a problem, but on most cameras you can correct that. But if you have no lens distortion, then if the camera is pointing to the nadir and is high enough, then all the objects have an object of the given size has always the same number of pixels wherever it is on the image.
It's right at the edge.
Yeah, I mean, if it's no lens distortion, then the camera could be assumed to be rectilinear, something like that, I think we said. And it's supposed to be okay. Yeah, and you can check that. I mean, so in Fudaa-LSPIV, you can enter several distances and you will have the resolution associated to each segment. And if you do it, you can check that it's working fine if you don't have any lens distortion. And if you have angles also, so if the camera is not pointing nadir, then it will change also.
That's what the error is. Pixels scaling. Once you scale that, and you find out pixels 5 centimeters, for example, then the error must be
yeah.
When you measure your check.
Someone in the chat asks, where can they get your software? Okay, so if you just Googleize Fudaa-LSPIV, you will find it. That's the best way to have it. Or you can write to me, of course. I'd be happy to answer. But no, but the software is, I mean, it's free and you can just find it. We have a web page, not a web page, a place where the software is. And it, I mean, if you Googleize it, it's all pretty free. Google us software. Thank you. Thank you.
Everything just kind of shifted. But after now, you may really just crack on with this and go for the course. Get Michael to
Yeah, no, yeah.
because that's the last presentation in session 2. So before we have the coffee, the Zoom. Yeah.
Sorry. Just need to. Yeah, just sharing.
Okay, great. I'm Michael. I'm from the University of Sheffield. I'm also an acoustician, so I'm doing effectively trying to tackle what you guys do with images, but on a much smaller scale and acoustically. We've next slide, please. We're going to go through some stuff. So I'm going to peel back the H kernel and show a little bit of what that is. It's a big integral. And we have 2 cases. We've assumed in this whole thing to simplicity, and I can visualize some stuff to show you. And that effectively, I'm assuming that where it's 2D and we have average, we have a constant depth below, we have a constant average velocity, just to make things clearer, to make sure there's no reason why this wouldn't work with a variable depth. You'd have to be a bit careful. I know when you're using the ADCP with Photogrammetry, you want to move around your beams, you'd have to be a bit more careful with the way you move it above the surface. Next slide, please. And also, please note that this is all synthetic at the moment. So this does work on data, trust me, please. I didn't have time to put it in the presentation. So why acoustics? We had some reasons about why we care about this stuff. Why acoustics specifically? Well, as we hopefully I'll persuade you, this works in low depth environments between like 1 centimeter to 50 centimeters. That's the region that you care about in terms of the depth. And also, it's a traceless way. We like traceless ways. You don't matter about the color of the water or if there's traces present. And yeah, we have our own issues. Rain was mentioned earlier. If you think about a source in the air, this is a fluid. If you have rain, we now have particles moving in a flow in a fluid. So it then just acts exactly like an ADCP again. And now we're bouncing off these particles. So we need to be careful in those situations. So rain is a big issue. Wind, not so much, but rain much more. Next slide, please. Yeah, so next slide. So this was the kernel, effectively. And they said it's geometry based. It's geometry based because the only key factors here are R1 and R2, which is your distance to the point of the integral, and your source and your microphone. This A basically is just your directivity. So what source are you using? If you're using just a normal speaker that has a direction, this direction is based on frequency, and that gives you some indication of what illumination you have on the surface. So therefore you will know where your resolution is good. And this is all your surfaces at one point in time. And this integral, the key part about this integral is it's annoying, but actually it's really quick to compute. Like you can use trapezium or Simpson integral. It's less than a second to compute in 2D. It's about 5 seconds in 3D in full resolution. Next slide, please. And another layer that we hid away for moving surfaces is we don't have an instantaneous, accurate river system. So what we do is we have our dispersion relations. If our flow is moving faster than the way the surface where patterns perform is moving faster than that, we assume it's basically a vector. So we have this one, and this is the one we saw earlier. So this is the one in the presence of gravity waves, gravitational waves. We have this term here, which is the same as we saw earlier. So we have gravity and surface, surface tension and your density, and that's where your depth is there. So if you don't have gravitational waves, you can't recover your depth. So that's another limitation. So the way we form it, we get these random numbers. We put these just put the wave number, we put the dispersion relations inside, inverse Fourier transform it to get back into space, divide by standard deviation to make sure it's RMS is 0, then tap 1, and then we times by our amplitude factor. That's the way we're kind of hiding it all. And this is the secret scale again, this minus b/2, which is a turbulent recognition. We're looking at that. When I said surface slope, we're looking at recovering that beta. And this delta is your altitude, and then these are your velocity and your depth. So that's important. The next slide, please. Now, so the whole result of what you saw earlier in piecemeal, any surface, when you then take the frequency minimum structure bit, should have these types of structures. So you have this line on y equals x effectively on your frequency window spectrum, which is your advection, and you have these two extra curves on which go like this and then down, which are your upstream and downstream gravity capillary waves. And what we'll see is when your velocity changes, this rotates, this shape rotates, and when your depth increases, this slight region like moves a little bit. Next slide, please. So to convince you that this does work at low depths, we can take the derivatives of the gravity capillary waves with respect to velocity and depth. Velocity expected is obviously linear, so it's very sensitive overall. Take the derivative of the gravity capillary waves with respect to depth, and you increase depth and you look at all the wave numbers. Apart from 0 wave number, which is infinite waveform, really the only information sensitivity is below ½ a meter. And it's better the lower down you go, so lower depth. So this is, if you're above ½ a meter, there's not much room for sensitivity in terms of recovering depth. Next slide, please. Yeah, so the whole reason this works, it works exactly like the Doppler ADCP. You're exciting a source that's stationary on a moving surface. The particles that make the surface are moving in a certain direction, which is related to the flow velocity. We then receive that at one microphone. In this case, we're only doing one microphone. When you're doing 3D, you want more than one microphone. Ideally, you want it in the grid. And we just get the Doppler shift, and that information of how the energy is separated from its carrier frequency is where it has the information about the speed, as well as the depth and the amplitude. It's all carried in that information, which is why rain is such a problem. It affects Doppler shift, it affects this whole thing. We get Doppler shift simply just by taking the power spectrum of the signal. Next slide, please. So a lot of maths, fundamentally, if you have a source and a receiver, as the surface, this is a water surface, as the surface moves along, if you get rid of the carrier frequency oscillation, received signal from the microphone is going to oscillate with respect to the illumination zone at some point in the surface. You can widen that illumination zone by adding more receivers. You can shorten it by having one. We only have like a really small region of our illumination. Once we have that time series, we can then get the Doppler spectrum from that. And this Doppler spectrum has everything we need. Next slide, please. Again. So we have two cases. What I'm testing here to showcase that some stuff works. We're going to have a linear array of a source and receivers. We've got flow moving in one direction. This case is moving towards the receiver. It's airborne by about 30 centimeters. We're looking at 18K. The velocity changes, not very physical. I'm not a very physical person. Between 0 meters per second and 3 meters per second, depth from 0 to 0.5, and the surface slope, which is effectively your turbulent structures, between 2 and 6, which relates to 1 and 3, because you divide by 2 after the fact. Okay, we have ranges. I like doing machine learning. Uniform generated data. We get 10,000 random generated data. I believe last year I used random forest in a talk for surface velocimetry last year, and I went into detail about random forest more specifically. So either go back, I think it's on YouTube, or better way, go to the experts on scikit-learn. It's the most introductory text of machine learning, just in terms of application in Python. Next slide. So we've now got 80 kilohertz cases here. So we've got these different amplitudes of depth, as well as the surface slope. So this is the recovery from the model. This is the true parameters on the x-axis and the predicted on the y-axis. This blue line is perfect reconstruction. The orange line is a line of best predicted data. The issue in case one, when you've got low frequency and you try to vary the surface slope, the depth isn't recovered at all. It's such a sensitive, small change that you need to know quite a lot of things if you want the depth in any good capacity. Velocity is very nice. Velocity is the easiest thing to always recover. I usually try and get something more than velocity, because velocity is, because it's directly in the Doppler shift, you can see it very simply. And the turbulent structures, if we vary it, we can get it accurately, but this is the first one to go in the presence of noise. This is just the noise-free case. I've added some noise here. We've got some metrics for the coefficient of determination. 1 is a good number. I mean, absolute percentage error, lower is better. I mean, absolute error, lower is better. You can, I can share these slides to go into more detail later. Next slide, please. So obviously it's synthetic, which is a big problem, because when we're outside of our region of our frequencies, we've got no acoustic data there, which does not make any sense. So we can add noise to each frequency, and it basically just means that if every frequency has some signal, the noise floor is going to raise up based on the noise. And And we're going to have four different cases. I'm only going to show the last case because that's the case where it fails. There's results on the table for all of these cases. We're only going to show case 4, which is the highest noise. Like this. And what we see, we've established in this case that the depth doesn't work, so that's fine. Surface slope is now gone, and the velocity, again, the most important information about velocity is kind of the spread of the Doppler shift. So if the noise floor, as it's raised higher, interrupts the spread, then you're going to break down. In this case, it's broke down between 1 meter per second and 2 meters per second. It comes back because now it's wider again. So if it's really thin, if you're looking at really small velocity, you can deal with a higher signal to noise, lower signal to noise ratio, higher noise signal. But the more you try and get in a range, the more you be a bit careful because the shift is going to carry through more. This table just shows all the noise cases. I'm not going to go through it all. Effectively, noise goes up, these scores go down. It makes sense, but not by much until the last case. Next slide, please. Now, case 2 is effectively we're just swapping it around. We're going to move the surface to the source, and we're at a higher frequency. 1, because this is where we've got actual data, so we're getting results from it. 2, probably don't want to showcase something that people can hear quite loud. Might as well try something that isn't humanly audible. With the same geometry roughly, so you're looking at much further acoustic wavelengths away, where you'd expect it to maybe decay a bit more. So next slide, please. But at this frequency, I've lowered the depth down to 0 to 0.2 meters because past that it breaks down, and just from that sensitivity graph. And velocity from 0 to 1. And now, instead of doing the surface slope, I'm fixed that because of turbulent structures. I'm just assuming it's minus 7/2. And I'm now getting the RMS height of the surface as well, so the actual surface elevation, which could be important for monitoring. So I'm getting that from like 0.4 of a millimeter to 2 millimeters, velocity from 0 to 1 meter per second, and depth from 0 to 0.2 meters per second. This is all noise free in here. Velocity again, it's when you're looking at Doppler, which I guess is the key thing, like the velocity change is the most sensitive system. It's pretty simple to make a system that works and gets velocity when you're looking at the acoustic Doppler. The depth, interestingly, if I cut it short at 1.5, it's got a wide spread, but it would have been really good. This is another indication of it's a frequency-based system. When you're looking at the sensitivity that's in this core, you need to be very careful about what frequency you're using, so you can excite different regions in the surface. If you've got a surface that's running, a rough surface that's moving at different roughness scales throughout the whole system, and you're at a certain acoustic frequency, that's only going to capture certain acoustic certain roughness scales in the surface based on the acoustic wavelength. So ideally, you could do multiple frequencies and then cover the short scales or the longer scales. So it's all dependent on that, and that's what goes through. Amplitude is good, velocity is good, depth, we're almost there. It's better off this. Next slide, please. Yes, feature extensions. I've gone quite quick. Real data is really important in this type of system. It's all good. It's all good looking at synthetic data, but actually, there's no verification of metricizing at the moment in terms of real world data. I've got real world data that's quite accurate that I'm working at the moment, and about most of them are working as I expected as across these numbers. Look, for receivers, it's very important in 3D in general. If you want to get a full, like Carol showed earlier, a full velocity profile in the streamlines and in the lateral directions, that you need basically a grid of receivers, and then you can correlate them spatially between each other, and then from there you can get the 2D velocity profiles from it. And yeah, more accurate surface modeling. You saw my surface modeling. It's not very physical in terms of it carries the information of dispersion curves, but not much else. And that's probably a key there. And that would encompass variable depths throughout, especially in 3D. When you're looking at, say, if you could pass a actual depth profile you've got from Velocimetry, then you would have something that's more physical. Whereas this is just kind of average throughout the whole system. Especially when you're looking at short depths, it's kind of important to make sure you have those Jacob scales. Well, that was quick. Thank you very much for having me. Any questions?
Yeah, I'm spinning a little bit full of maths and stuff. I don't know if just trying to get my head around it. How do you define the surface slope? Is it like is it a very small area, or is it of the section?
Yeah, so surface slope is probably not the best word to describe it. Effectively, it's the turbulence roll off in the wave number domain. So it's not actually the physical slope of the surface. It's more the way that where the surface rolls off in frequency. If it's more turbulent orientated, then you'll have a different. It'll be expected to be higher. Try to get that physically matching. Right. Yeah.
Real data. Should we become real data?
Yeah, but not.
I'm planning to actually use those data we got from say India.
Yeah, so Loxley we have access to at the moment. There's some issues in the full 3D reconstruction, but I think it's an issue on the modeling side of the data. At the moment, we're using. We've got some data from Bradford a while ago, which is the whole reason it's one receiver. To prove the concept, a while ago we put one microphone and one receiver to see that shift in Doppler. So I'm using that data at the moment because we have very, very accurate velocity measurements, depth measurements, amplitude, like RMS amplitude of those waves. So at the moment I'm using that. Again, that's then not at an actual real river, so we don't have variable depth, which is going to be a massive thing, especially when it's sensitive to really small, really low depth. Variable depth is going to be the most important thing. But at the moment, yeah, and those results are quite accurate at the moment, but I'm still in data processing. Each one seems to be a bit different. I don't know how much I'm processing out versus not, so I'm in that process at the moment.
Yeah, that was kind of the next question. Is there an opportunity to sort of see this tomorrow, or was this not to that point yet of going to the road system? But yeah, well, we were.
Did you pack an acoustic source, Carol?
I think machine learning is the right way forward. It's just how reliably we can train.
Yeah,
so
the training stuff.
It's good to look at this data. We've got plenty of them, tons of this data. Whereas in a lab. And you apply the random forest, but there's some millions of other.
Yeah.
So and also you apply it for Doppler. So they also can apply just basically plug it to the sound pressure for the microphone. Because the way they change the time and space of microphone also tells a lot about the surface roughness. And the surface roughness definitely leads to the flow condition. So when are you going to see it, Michael?
When are you going to see it?
Before you graduate with the
Yeah, I've got about half of them analysed and come through at the moment. I'm hoping that by the time I get back to Sheffield, the workstation will have done everything I needed to do, and I might have some results.
Okay, November.
By November, was about by Wednesday. Yeah, no, but yeah, real data is going to be the big problem, especially in 3D. It's the same type of issue that we're seeing in the data from we're assuming. That's the key point. And being out in shallow environments, because this is where it thrives, and try and model where you're in like 10 centimeter depth, where like a small pebble is going to make a massive change. Try to get that sort of mapping through. I think it's going to be the key challenge for this as it goes forward. But it's really useful, especially if you're looking at shallow water over bridges, say UK. That getting the system under there, this would be perfect. Just if it works.
So let's go back to the surface slope thing again.
Yeah.
The relationship between, I guess, the river gradient and surface slope. Is there a limit there? Maybe things start getting complicated, almost taking them towards waterfall and territory.
I'm not sure. Simon might know more than me.
Trying to get my head around it, the way it works.
Possibly because the way in which the turbulence generates your velocity profile changes.
I mean, you wouldn't want to try and measure the flow of a waterfall anyway, using this technique, but just theoretically, I'm just thinking there's a kind of a tipping point.
But you might get a very steep channel on a very shallow depth. And there the turbulence would give you a very sort of velocity profile. Would affect the roughness challenge one to see all the line. And that will give you a different. So, yeah, something like that. Yeah. So something would get it done very fast. You have to, but I've seen the big others very slow, but something that's very.
Yeah, I mean, good to put in your PhD, same trial based on your data.
Yeah.
So it'll be like a last chapter section.
You can, sorry, you could imagine that very thin was very turbulent dominated, whereas the very deep was dominated by air gap. Probably not smooth progression. I think we would jump from one to the other. Yeah.
Just a thought about sort of background noise without an active source. So I guess it's a bit left field from what you presented, but you know, each of our sites has a different noise characteristic. Just visiting the different flows, you can just hear the noise of the river. Do you think the scope, if you had 1,000 measurements of noise and velocity, to just sort of eventually understand the site-specific background noise characteristic at different flood levels, velocity? Probably very site-specific, I guess. But
Yeah, it would be
machine learning approach of a big data set.
Yeah, it'd be more like acoustic soundscaping. So you would go through responses. I don't think you could use this type of approach to do that. If you were trying to say get the response of your system to the flow, filter that out or model that, and then be able to use that somewhere else. And so you've got your own channel modeling software. You have this dynamic. This method doesn't directly help you with that. But there are methods to kind of like, for instance, like room acoustics is a big thing. Soundscaping is quite popular.
It's good thought that the very site specific.
Yeah.
The way it knows where it makes is due to the cavitation. The cavitation is very local phenomenon. So as a result, it may be very complex relation between the site and the noise of the site. Over time, probably can train, but that pattern can change.
Oh, somebody had done that, was it in the online workshop 2 years ago? Somebody presented it, not University.
Yeah, it was researcher at Durham, who's still listening. Said he was trying to get water now. Yeah, quite interesting. I think for this chart, there's a potential inside monitoring. Like to explore.
Yeah, very measured vibration. So, it's some correlation with the geophone and the sound that is done by the vibration is will be involved in Florida and the shadow vibration. So it can be separated from the shoe.
Great, a lot of projects.
Okay, so 15:15. So we just say thank you to Mike. Okay, I think we take over there. So I'm going to do one more question. Right?
Well, finally, go is
So we're supposed to come back at 15:15, which is again, so fucking on. So will you talk now?
should be short than that. Make it time.
Well, we should documentation in Fudaa-LSPIV. It was fair playing if we do.
It's not that in 20 minutes, which is are you right to recommend it?
Yeah.
Make it a nice presentation.
Yeah, that'll be helpful.
Yeah.
Yeah, the 3D. We've got.
Yeah.